going to prove, or we're going to do problem C on the adventure sheet on group actions. So this is where we start with a group acting on a set X. And so in the first part, we want to observe that if you fix an element G in the group, then the rule that assigns, or that maps X to G dot X, where G is acting on X, we want to show that this is a function from X to X. Okay, so first of all, what do we need to show that this is a function from X to X?
So it is a rule, but we should check that this is in X, right?
Okay.
And I don't know about the well-defined.
Yeah. But maybe before talking about well-defined, I think that you're right that this is an element of X, though. Because that's what it means to be a group. Maybe let's remember what it means to be a group action.
Okay, so group action was you have a function. So I guess we know that this is a function that took an element in the group and an element in the set you're acting on and took it to something like this. And what were the properties that they satisfied?
I think the first was that the identity acting on X just maps to X. So the identity is like change X.
And this was for all
X.
Okay.
Yeah.
In the set.
And then the second one is like function composition sort of. So if we have G and H, we shouldn't share chalk. G and H in our group, then G dot H dot X is equal to GH dot X. So it's sort of like associativity, except X doesn't have to be an element of the group.
Should there be a die here, or why is there none?
Oh, because this is an element of the group. So like G and H are in the group.
And so we're reserving the dot for
the dot means like you take something in the group and do something to X.
Okay.
Okay, so this is our definition of group action.
So then this is definitely an element of X.
Yeah, because that's what the group action means. Okay, so that's an element of X. And you said something about well-defined. Do we need to show that this is well-defined?
In this course, whenever we have to prove that something is a function, oftentimes we have to
prove that it's a well-defined function.
Yeah.
But we have to do that when we're mapping like a set to a set. Or like a set of sets to a set of sets. And here, X is just a single thing, so it can only map to a single thing.
Mm-hmm.
And this is the single thing it maps to.
Okay.
So I think that this is not
we don't need to care.
Yeah, I think all functions are well-defined functions.
Okay, so the only thing we needed to show is that this is an element of X, which was because of the definition of group action. Okay.
Okay, and we're also told that we should denote this rule by add G. So add G is a function from X to X that takes X to G dot X.
Awesome. Okay.
Okay, and then we want to show that add E is the identity function. So what is add E?
I guess we have a formula.
Yeah, we have a formula. So add E. It's a function from X to X. It sends X to E dot X. But we know what that is.
Okay.
And this is X. And so this is the identity function because X gets sent to X. Okay, cool. So this is property 1, essentially. Okay. Do you want to do 3?
Sure.
Yes.
Okay. So I guess we want to show that this is a composition of functions, and this is another function. We want to show that the two functions are the same. And the way we do that, we want to compute this, and we'll also compute this separately and see if we get the same thing. But I guess maybe we should take an element in x and have the function be evaluated in that element.
Oh yeah, this is how we show that functions are the same as we look at what they do to things.
Okay, so I guess I'm let x be in x, and I'm going to try to expand this out.
Okay.
Okay, so I guess maybe I should write, because I always get confused when composing functions, so like, and there's a lot of parentheses, so maybe if I have two functions, f and g, g maybe as well, because we're using that.
Oh yeah.
Okay, so maybe,
F and H.
but we also have h.
Darn it. F and J?
Okay, if we have two functions, f and j, and we apply it to an element here, this was f, and you evaluate that
At J of X, yeah, that's right.
okay.
So I think what that means here is that this means that we're doing add of G, which is a function.
So that should be your f.
Yep, evaluated at add of H of X.
I think so.
But we know how to compute add of H of X because that's what this rule is.
Oh.
It means that we have H dot X. And then we take add of G of H of X.
Yeah, this is an element.
That's an
of x.
element of X, so we can plug that into add of G. And so what that is that's just like G dot H dot X.
Oh, it looks like this.
Yeah, and I think, yeah, that's reminiscent of our second property. So this feels a lot like the second property. GH dot X. And I guess that's that. GH dot X. That's
Oh yeah, it's
Like
literally plugging gh instead of g.
yeah. So basically 2 was property 1 and 3 was property 2. This is add. Thanks, Ava. GH. X.
Alright, so for all x, we have computed, we started from the left-hand side and we got to the right-hand side.
Yeah, and
Okay.
because that's true for all x, that means that these functions must be the same. Because they do the same thing to all elements of the domain.
Yeah.
Okay, cool.
And we're done
Let's
with 3.
let's move on to 4.
Where should,
Let's
here?
do it there, I hope. Oh, okay, so with 4, no, keep going, keep going. I'm excited about how 4 is different. So now we're thinking about add as a map from G to bijections of X. Yeah,
What is
add.
that?
Yeah.
Add, like,
G, yeah, to the bijections of X. Bij.
Oh, okay.
And I guess it's going to be defined where you send G to add of G. And we know what add of G does.
So, what is the question?
Oh, yeah, good point. We want to show that this is a group homomorphism. Okay, so first of all, if this is a group homomorphism, that means that it's implying that bijections of X are a group. So, do we believe this?
Bijections are functions,
Okay, great,
so we can compose them. I guess that's the natural way of.
great. Okay. So there's a group homomorphism. So bijections are functions. There are group. Excellent.
Like this.
Okay, cool. I like it.
Okay.
And so we want to show that this is a group homomorphism. What do we all need to show? We need to show. Okay. Well, I know what we need to show. We need to show that.
So I'm sorry.
What's up?
I'm a little confused. I feel like I can see that this is a function from x to x, but not that it is bijective. Like if it said functions, I'd be like, okay, I understand.
Oh shoot! I didn't even think of that. Yeah. Why does an element of G have to map to a bijection of X and not just some function of X? Okay, so we want to show that these are bijective.
Okay, so let's outline what we need to do. The first thing we're gonna do is show that add G is bijective. For all G, because for every G it has to lie here. Okay.
Okay, so what is add G? It's a function, and I want to show that it's a bijective function. So add G. So is add G from x to x defined by sending x to G dot x bijective. So first of all, is it injective? So can we show that the kernel is 0? No. What?
What's the identity index?
Okay, maybe that doesn't make sense.
Yeah, X is just a set.
Okay, yeah, it doesn't have an identity. Okay, so this kernel thing is not helpful here.
So we gotta go with the definition.
Darn.
It has to be harder. So we need to show that if add G of can I write in some place what this means for functions in general, like I did here, and then translate it? Because there's too many parentheses. I don't know where.
Let's do it here. Maybe.
So for injective, what one needs to show, like for a function f to be injective, is that if fx is equal to fy, then x equals to y.
Right.
Okay, and now f, the thing that we want to show is injective, is add g.
Yeah.
So
we just want to show, so we replace f with add g here. So we should say add y.
Add g, y.
Oh, add gy. Yeah.
Oh,
and we know what these are, right?
Okay, but we need to show that if these are equal, then x equals to y.
Yeah.
Okay, and now you're saying that we know what these are?
Yeah, we know that this is g dot x. And we know that this is g dot y.
Oh, yeah, right. Okay. So we want to cancel the g somehow.
We want to cancel the g's. But the g's are in a group, so they have inverses. So we can multiply on the left. G inverse g dot x. Can I do that?
I think so, because like g inverse acting on gx, we said that by the property 2 of group actions, you could sort of group these. There's a dot here. So it is that.
Great. So I'm using property 2.
Uh-huh.
And that makes my life a lot better.
Oh,
the fact that
that
E. property exists. Yeah, and this is E. And I guess this is property 1. That that says that this is X and this is Y. That looks like an X, which it is.
So
So we
That's
showed that
it.
it's injective.
okay.
And then what does it mean to be surjective here?
Okay. Okay, so maybe let me write again the definition for a general F. So F is surjective. F from say A to B is surjective if for all element of B, then you can find something here that maps to it.
Mm-hmm.
So there exists A in A such that FA equals B. Okay, but now G goes from X to X. So I want to show that for all X in X, there exists Y in X such that G Y is X.
Okay,
No?
so this is just an existence proof, right?
Yeah. So we
So
just have to find.
we just have to find something.
Mhm.
So what's the something we need to find?
The Y.
Well, yeah, but like, what's the Y that we are looking for?
Okay. This was G dot Y. So we want to find something that satisfies this.
Mm-hmm. Oh, maybe we can do sort of the same thing we did with injectivity, where we multiply
Right.
on the left by G inverse. It's not really multiplying though, like it's kind of group acting, but it's sort of but it cancels like it's multiplying. Or I guess it's like group acting. But okay. Yeah, okay, so here's my confusion, is like here I want to multiply so that I can cancel this G. Then over here I can't multiply because that's not an element of G. But maybe I can have G inverse act on both sides.
Okay.
Is that allowed? That I can just like make G inverse
I think you can.
act?
I don't know if that will solve an equation, but you can. The group can act on the set, and
Okay.
this is in X, GY is in X, X is in X. So you can. Okay, and there was property 2 that said that you could group the things in the group.
Yeah.
And this is EY, which is what?
Okay, so maybe the Y we want is G inverse dot X.
Okay, so our candidate for Y is G inverse dot X. Like, if Y exists, I guess we've shown that it would have to be it.
I guess so.
But
why don't we check that it
yeah,
works?
that's
So if we take add G of G inverse X, that is G dot G inverse X. That's weird. It's the opposite order that I did there.
we can still group them.
Yeah, I agree. G inverse dot X, and this is the identity dot X.
Okay.
That's X.
Yeah.
Okay, so that works.
Oh yeah, because this was our Y and we wanted to.
Yeah.
Okay.
So we showed that there is a Y that gives us X,
Which
means we showed that it's surjective.
Yeah.
Okay, that was.
I lost track.
Yeah, that was a lot of work. But I think we took a break from showing that this was a group homomorphism just to show that the that the codomain was the right set.
Yeah.
Okay, so I think we want to get back to showing that it's actually homomorphism. And I know what that means.
Okay. So I can erase maybe all of that because this is something we did.
Okay, sounds like a plan. I'll erase this.
Okay.
Oh, there's only one eraser.
Mhm.
Bummer. So I'll let you get started on showing us a homomorphism, I guess, and I'll
Okay.
erase.
So now we need to, now that we know that it's the right codomain, you said show that it's a homomorphism. Okay, so that means that we need to show that if you take a product of two things in G, then you should get the product of the adds.
Mm-hmm.
So add G times add H.
Yeah, this seems a lot like the second property of
Oh,
group
but
action.
times is composition.
Yeah,
It's
yeah,
right
yeah.
here. Okay.
This seems a lot like the second property of the group action, I think.
Oh, that was part 3. We did this.
Yeah, we did.
Okay.
Awesome.
So
Part
this
3.
was part 3. So the gist of this problem was not the group homomorphism part, but the codomain.
Oh well, I'm glad you caught that because I thought that part was. I thought this part was easy, and I guess it was easy because we did it already.
Yeah.
Okay. So let's move on to part 5, which says that this add that corresponds to a given action is injective if and only if the action is faithful. And I'm going to use this notation from Becca's mini lecture. G acting on X is faithful. I have the sheet if you want to see it. Okay, so let's remember what it means to be faithful, maybe.
Yeah.
So a group action is faithful if G dot X equals X for all X implies that G must be the identity. Is that right?
Yeah.
Did I get that right?
Here it says if the only element G such that EX is X for all X is the identity, but
That's the same thing.
the same thing. Okay. Okay.
Okay. So we're also trying to show that add is injective
So maybe let's translate what it means
in our context.
Oh, but add is now a group homomorphism, so we couldn't do the kernel.
Oh, great. Add is injective if and only if the kernel of add equals the identity map. Maybe I'll say this. Identity map.
No, the identity here.
Oh yeah.
So yeah.
I'll say E. Maybe I'll put a sub G just so I don't
Okay.
forget where it lives.
Set.
Oh, thanks. Okay. And what does that mean?
Okay. Well, the kernel is the set of elements such that add G is the identity here, but that was the identity transformation, like you were saying.
Oh, and the identity transformation is the transformation that takes every element to X. So, so this is like the G in G, so that
Gx is equal to X? Because
I was gonna say add G
X.
X
Okay, yeah.
equals X, but you're right. This is G in G, so that G dot X equals X. Is that right?
Okay. So many equalities. So, but I guess recapping, we've shown that add is injective if and only if the set this G equals Gx equals X is EG. Because this was an if and only if this thing, which is this thing, was equal to this thing.
Mhm.
Right? So, okay, we have this. This is what it means to be injective. And we have this, which is what it means to be faithful.
Yeah, they're the same type. I added for all X.
Oh, yeah.
To my universal quantifiers.
That's right. Okay, so now that we have the for all, this line and this line mean the same thing. So this thing and this thing are equivalent.
They're equivalent.
And we don't need to go both ways.
Yeah, we everything was equality or
Uh-huh.
if only if statements.
Okay.
Awesome.
Yeah.
Air 5.